exam problems. So I will change the problem, and there are some sample problems that you can find from my website. So, excuse me?
That's the actual test?
This is the actual test, but I will print differently on the exam. So on the exam, these are actual tests. So to access the exam file, you go to my website. Now, of course, after this explanation, I will really go to the website. You go to my, and then in number theory, you can click on this info. Then this will be linked to this website, and here you can find the sample test information, A, B, C, D type, and the actual exam will be similar to these things, not exactly the same, but similar to these things. And also homework days you already accessed. So let's go to that site. But I will pause so that you can write down the information. If you have a question about accessing it, accessing these sites, ask. So go to my website, click on info to go to this place. And once you are in this place, so let's do it. Once you go, so how can I come to my website? Once you come to UCCS, you can come to math site, right? You can come to math site. Once you come to math site, you can come to people, and then people you can find me, and then you can come here, right? So once you are here, you click on info to go to this site, and then you can access many things. And then also you can access video archive files of the lecture covered here, and other things too. And here you can access type A, type B, type C, type D. So for instance, type A is here. So you can access this thing and then print out the sample tests and then practice. And then, for instance, D, you can access D, sample D. So these are samples, and the actual exam is right here. And then I already made the problems. I will not change the problems. Already made. And I will print these things differently on the actual exam. These are the problems. Any questions about the exam itself? Not the questions, but exam itself. Then, one more time, it is 2 weeks from today, right? 2 weeks from today, and the same time in this room. And the coverage is from section 1.1 through 3.3, or up to page 59. And I will collect the second homework on Wednesday next week, a week from today, right? And then on the exam day, you submit your homework on the exam day. But if you have questions about homework-related problems, you can ask me before, right? On Tuesday or Monday, you can ask. Any questions? Then let's continue covering this top part. Roughly, in number theory, there are two different groups, addition group and multiplication group. Addition group is covered in, addition group was covered in the previous two chapters. Now we are covering multiplication group. Then when you multiply numbers, then we want to extract the very, very basic thing called the primes, right? So we want to extract prime numbers. So prime numbers is defined by this. The divisor should be 1 or itself, right? Then it's prime, right? The divisor is 1 or itself, none other than these two things. If you have other things, then it's not prime. So it's the definition that you can find in the book. Then under this assumption, we want to write many nice things. And first thing that I want to write is this thing that I covered last time. If P divides product of two numbers, prime P divides two numbers, then P divides A or P divides B. So this is nothing but the application of Euclid lemma. And more general case can be mentioned. If P divides product of many numbers, n1, n2 up to nm, then P must divide some nk, right? P must divide some nk as a corollary, and we covered up to this point. If you want the proof or want to ask any questions, ask me. Then, as I mentioned, I will slowly cover the prime numbers. So what are the prime numbers? First of all, is 0 a prime or not? By definition, 0 is not prime. In addition, 0 is a product of many numbers. For instance, 5 times 6 times 0 is 0, right? Or any possible combination can come here. So many numbers are divided with 0, so it already violates the condition that defines the primes, right? There should be exactly two divisors, exactly. So I will emphasize this fact one more time here. Exactly two factors. And if we have more than two, or like one, exactly one factor, then it cannot be a prime. Exactly two factors. So 0 is excluded, right? What about 1? 1 doesn't have two factors, right? So excluded. 1 is excluded, right? Only one factor. What about -1? Negative number cannot be prime. So these are all excluded. So prime numbers are integers satisfying those conditions, and we excluded 0 and 1. In the past, as I mentioned before, even 2 was excluded when people considered prime. So definition part is done. And the next thing that I want to mention is the fundamental theorem of arithmetic. So I will write the acronym instead of writing the full theorem. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic says if we have a number, say n, then n is product of prime 1, prime 2, and so on, up to prime some number, right? This k is determined by the number n. So this is the fundamental theorem of arithmetic, and we can collect the same prime numbers. For instance, p1 might repeat right here and here and here. So p1 to the power of, for instance, exponent 1, and then p2, and then power exponent 2, and so on, and then pr e to the power of r, right? So r depends on the number n. So there are two forms, but essentially these are the same. And up to the order, this representation is unique. We don't prove the details of this theorem, but we at least know the theorem itself, fundamental theorem of arithmetic. So let's apply. Pick some number, for instance, 36. Then 36 is 2 times 18. 18 is 2 times 9. 9 is 3 times 3. So we can write this number in this form, right? The fundamental theorem of arithmetic is nothing but this decomposition, and then we can write it this way. 2 to the power of 2, 3 to the power of 2 multiplied. Any questions? So we now know very important theorem, fundamental theorem of arithmetic. And when we cover just the simple thing, you do not know why it is so important. But when I mention about the future usage, then you will see the importance of this kind of theorem. For instance, we want to prove some statement for general n. Or a theorem for general n, then it's not easy to handle general n. It's not easy to handle general n. And what you do is, using the fundamental theorem of arithmetic, and then using the fundamental theorem of arithmetic, we decompose the number n into this pattern. Then we prove the theorem not for the general n, but for the prime power. In other words, instead of proving the theorem for n, we prove the statement for prime power, right? Then later, for generic prime, after proving this for generic prime, later we multiply these things to prove for n. So this is the direction. In other words, fundamental theorem of arithmetic is used in the proofs, in the future proofs, not now, later, we will handle this kind of case. So in the future, I may ask you to prove something for n. Then all you need to do is proving it for prime power. Why? Because of the fundamental theorem of arithmetic. Why do we care about primes? Because prime is relatively easier to handle. What are the possible divisors, assuming that we have, instead of symbols, let's use numbers. Assume that you have 2 to the power of 4. What are the possible divisors of this number? Possible divisors, smallest to the largest order is what? 1 is the divisor, right? What else? 2, what else? 4, right? Or 2 squared. What else? 2 cubed. What else? 2 to the 4. In other words, when you have a prime power, the divisors are very straightforward. Total 5 possible divisors of 2 to the power of 4. Then by just considering these cases, we can prove some statement. So this is the key idea. So fundamental theorem of arithmetic itself is important, but more important usage in the course is using the fundamental theorem of arithmetic to prove some statement for general n. We decompose n into prime powers, then we only consider these kind of things. So I explained the reason. Then the next thing is the fact. I don't want to call this theorem, but just a fact. It's not rational or it's irrational. So prove that square root of 2 is irrational. When I first heard about this question, how can you prove it? That was my response. How can one prove this? That was my response. So I will give you at least one proof now, and then if you want more, then I can give you second proof. But one proof will be enough. Rational and irrational is defined by one thing. Integer over integer, then rational, right? If it's not possible this way, then it's irrational. That's very simple, right? Rational means integer over another integer. But if it doesn't happen this way, then it's irrational. So we want to prove this thing by contradiction. So as I mentioned before, from this chapter, you will see many things by contradiction. And it will happen at least 50 times in the course, at least 50 times in the course. We negate or we assume that the statement is wrong. And then we lead to a contradiction. And then return back to the assumption. In other words, because of a wrong assumption, we got very strange contradiction. That means our assumption was wrong. In other words, the statement that this statement is wrong. So that kind of a little bit confusing. But once you are familiar, you train yourself, it will not be very tough. So how can we begin? Once we are asked to prove this thing using contradiction, then this is the starting point. Assume not. This is the short statement, but I will re-describe it in the next column. Assume that it is not true. In other words, I will restate this statement. Assume that square root of 2 is not right, is not irrational or is rational, right? Assume that is rational. I don't like to negate twice. So I say instead of square root of 2 is not irrational, I said square root of 2 is rational. Then, what can you say? Square root of 2 is an integer over another integer, right? Do you follow me? Integer over another integer. Or it's not a good idea to write int. So I will say, I will use two letters. What letters do you want? You pick two letters. I will use your letter. P and Q? Or M and N, I and J, anything can be used, right? So assume that square root of 2 is P over Q, where P and Q are all integers. In this chapter and exams, I didn't even say the letters are integers. I just said prove this, prove that, without saying they are integers. All these involved letters are integers, right? In this course, in this section and chapter, these are all integers. So assume the square root of 2 is P over Q, where P, Q are integers. Then I want to square both sides. Then if I square both sides, then 2 equals P squared over Q squared. If I multiply both sides by Q squared, then 2Q squared equals P squared. So I want to conclude this thing. P is even, right? P is even. Why? If we have odd squared can be even. Odd multiplied twice is odd, right? So it cannot happen. So P is even, and then P equals even number 2 times K. Do you follow me or not? Because of this.
Is this a case? P is even?
Excuse me?
Is this a case? Like P is even?
Because of this reason, P squared is even, right? P squared is even. Do you follow me?
Okay.
P squared has 2 factors, right? So, because P squared is even, P should be even. If P is odd, then odd squared cannot be even, so P is even. I will be slow, so if you have doubt or if you want me to describe the details, then I can describe the detail. So P squared happens to be 2 times something, meaning P squared is even, then P should be even. If P is not even, then P should be odd, right? Even or odd. If P is odd, then odd squared cannot be even. In other words, it cannot be odd. So P is even. But before going further, I will write one more condition. When we wrote down P over Q, where the GCD of PQ is 1. This is the condition that we will need. So now I use the general statement and then add the condition. It is very legitimate to add this condition, but if you don't think so, challenge me. Yes?
Well, that just means that P and Q are relatively prime.
Right. If not, for instance, assume that you have 10 over 20. Then 10 and 20, the GCD of 10 and 20 is not 1. They are not relatively prime. Then what can you do? Right. Then you will get 1 over 2. So no matter what, when you have a rational number, we can find the reduced form, right? With GCD equal to 1. So you need all these things to prove it, right? In this direction. In other direction, we can prove differently. But in this direction, you should prove. Then, now, we replace P by 2K. We replace P by 2K, right? We replace P here by 2K. Then 2K squared, right? 2K squared or 4K squared. Do you follow me? 2K squared or 4 times K squared. Then equals the left side 2Q squared. If we cancel out 2, then Q squared equals 2K squared. Because of this reason, by the same reasoning, Q is even. So Q should be equal to 2 times some number such as L. The same reasoning. Then now let's find the GCD. GCD of PQ equals GCD of PQ equals GCD of 2K, 2L, and then GCD of 2, so 2 times GCD of K and L, and then GCD should be greater than or equal to 1 at least, so it is greater than or equal to 2 times 1, that is 2. GCD should be greater than or equal to 2. Initially we started with the condition that GCD is 1, so a contradiction. In other words, we create a contradiction thus assume not is right, assume not is not right. Thus assume not statement is not right. But people usually do not write this statement. People omit the statement and then people omit this statement and just say a contradiction, thus done. So proof by contradiction, the biggest goal is getting a contradiction. Any type of contradiction is possible. So once you arrive at a contradiction, then done. Or if you are kind enough, then you may write down thus. So there are 3 possible ways. The best way is this top one. Thus, square root 2 is irrational. This is the best thing because people reading your proof may not know what you are doing in the end. If they want to know, they should return back to the first statement. But if you re-describe it, then you are kind, right? And people know what you are doing. So thus square root 2 is irrational. So 3 statements are possible. This is very, very straightforward one. This is very straightforward. This is very short one. This is very kind one. In any case, I proved it. And please check this proof using contradiction. Have I ever used proof by contradiction in class? I might not use, right? This could be the first time. In any case, try to read from the beginning till the end and ask questions. Is this the only way to lead to a contradiction? There could be many different ways. When I grade your result on the exam, I may see very nice proofs, very different from the known things. There could be many different proofs, and if you want, I can show you another proof. But if you don't want more proofs, then I can continue. So it's your choice. Do you want another proof, or this is good enough? More proofs or good? Excuse me?
No more.
Great. Then let's go to the next case. It is the next section, 3.2. This is very brilliant method, the sieve of Eratosthenes, and the guy created this idea. He wrote down all the numbers. 0, 1 are excluded, right? 0, 1 are excluded by definition. And then wrote down the numbers systematically. And then he tried to find all possible integers satisfying the prime conditions, right? So what he did was this thing. He, instead of writing the prime numbers, he struck out non-primes. So I will strike out. Is this prime or not? Not by definition, right? Is this prime or not? Not by definition. Then this is prime, right? Then this multiple cannot be prime. This is prime. This times 2 is non-prime. So he struck out all the multiple of this first prime, right? All the multiple of first prime were eliminated. Do you follow me? Then the next prime is 3. Then all the multiple of next prime is eliminated. Then the next thing, 5. Then all the multiple of 5 is eliminated. And so on. So he can continue these things. Then, after this sieving, we get the numbers, right? So the remaining numbers are primes. So we can circle remaining numbers. We can circle remaining numbers to sieve primes. And so first appearance, we don't strike out. First appearance, we let it stay there. But from the multiple part, right? Initial appearance, we don't. So take a look. By definition, we removed. But the first appearance, we don't strike out. And we just strike out the multiple of this number, or 2 things. The next thing is 3. First appearance, we don't strike out. And the multiple of 3 is struck out. And then next remaining thing 5, we don't strike out. Multiple of this number, and so on. So do you get the idea? So this is a brilliant idea he developed, and using this you can find many primes. So I will show you the problem. So for instance, here, find all prime numbers. Then what should you do? You should strike out the numbers, right? So I want to find prime numbers from 0 to 69. So let's do it. So you may do it on your own. Initially, we should strike out the 0 and 1 by definition, right? Now I will strike out. 2 is the first occurrence here. So all multiple of 2 other than 2 itself is struck out. And then 3 is the first appearance, right? Then all the multiple of 3 is being eliminated. Any questions? Then the multiple of 5 should be eliminated, right? So multiple of 5 is eliminated. Right? And then 7 is here. Multiple of 7 should be eliminated, right? So multiple of 7, and then multiple of 7, and then multiple of 7, multiple of 7, right? So I eliminate all multiples of 7. And then multiple of 11 should be eliminated. So multiple of next number 11, then 11, and then 11, right? And then multiple of 13 should be eliminated. What is the next number? It's this the one, right? And then multiple of 17, 34, and then what is the next thing? 51, and then what is the next thing? And then multiple of 19 is getting harder and harder, right? Is this the one? 57, right? And then 27, multiple of 27. And then next number is too big. 69, right? So as you can see, you can extract and extract. And then after enough extraction, you may not get any more deletion, right? Then sieve these things. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67. So how many did we see? 19 numbers, right? 19 numbers.
Can you write a program to do that?
Of course, it's possible to do that, but we may use different method on other things, but it's possible.
So you can write a program to do that to infinity, right?
Computers cannot run forever, or it may run forever, but we may not see it in our lives.
It's one way to get off.
Yeah. So as you can see, this is the method developed very long time ago. In any case, I explained it. And if you have a question about this problem, ask me. If you don't, then I will mention about the next important property. But as you can see, how far should we go to eliminate? What is your guess? In other words, assume that you have numbers from 1 through 100,000. Then should I sieve from 2 to 100,000, or can we stop earlier? So what is your guess? Halfway meaning 50,000? Can we stop earlier? That is my question then. What is your answer? Can you stop earlier than 50,000, or 50,000 is the best that we can stop? That is the next question. In other words, when you use sieve method, we don't have to go all the way to the end. We can stop a little bit earlier or way earlier. I showed you the example that we can stop a little bit earlier, and someone suggested about half the way, about 50,000 we can stop. But can you stop earlier than 50,000 or not? So take a look. If we have any, I will define one term so that I can easily describe the situation. What is the opposite of prime? It is composite, right? So prime number, which is not a number which is not prime, is called composite. But we exclude 0 and 1 in this consideration, right? Or negatives in this consideration. So when we mention about prime or composite, we don't want to add 0 and 1 in the consideration. So just remove and then consider, right? So anything greater than or equal to 2 are the candidate for this consideration, prime or composite. So any composite number can be written by the product of at least two numbers, right? So some number is here, then A times B generally. A times B generally. Of course, A could be C times D, right? A could be C times D, but at least I wrote down two possible numbers. Then take a look. Assume that these AB factors are given, then a very unlucky situation is having the same number, A and B are the same, right? Then this number is nothing but the square. Then we need from 2 through this A, right? We need to calculate everything from 0 through A. After A, we don't have to see. Why? Because assume that some factor exists here, then smaller factor should have been considered before. Do you follow me or not? If you don't follow me, then I will slow down. So I will go to this situation. So let's consider the case such as this. Assume that n is 100,000. Then 100,000 is, I don't like 100,000. I like 10,000. I like 10,000. Then assume that n is 10,000. Then A equals B equals 100, right? A and B are equal to 100. Then what happens? From 2 to 100 we should sieve, right? From 2 to 100. But after that we don't have to sieve, because assume that some factor is such as 200, right? Such as 200 exists. Then there should be a counterpart here, right? Before 100, like 50. In other words, when we considered 50, we in some sense already considered this factor. Do you follow me or not? So when you see, we want to go as long as possible, but should we go over 100? The answer is no. Why? Because when we hit 200, then this number is nothing but the one that we already considered here. Because when you handle 20, then 20 multiplied by this thing was considered in 50 consideration. So this kind of situation. In other words, we don't have to go any more than square root of n, right? So the maximum number that we should go is square root of n, right? We can stop before square root of n in most cases, because most numbers are not squares. So when we sieve, you don't have to sieve 50,000 numbers. Square root of 100,000 can be considered about 3,000 might be enough. About 3,000, a little bit more, right? Then 3,000 will be enough to see. Why? Because when we consider 20, then we already handle the counterpart. In any case, when you sieve, we can do this. Then the next thing is, but if you have some doubts, then ask me. Assume that you are asked to sieve for 1 million numbers, then what is the maximum number that you should consider to sieve? About 1,000 numbers, right? Then you can strike out all the related factors down the line. But that does not mean we need to consider just, you should not be confused. That does not mean you can just consider the numbers up to this point. In other words, it does not mean that you should sieve for this number. It's not that meaning. It means only factor that can appear in the product belongs to this portion. That's what I meant. Do you understand what I mean? Or not? When you sieve, we should sieve all the way on through this number. But the factor that can happen is condensed in this region. Outside this region is not our major concern. In other words, assume that we have factor 1001. Then, how can you get this number? Assume that you have 1001. How can you get this number? Then it is some number, smaller number should be multiplied to arrive at this kind of number, right? So we eliminate the way of sieving. I will slow down. Yes?
So we're really just looking at, in this example, we're only looking at multiples of factors between 1 and 1.
One and right. Multiples of, yeah.
So 2, we eliminate all the even.
Yeah. Yeah.
When we go to 3, we eliminate all the
All your multiples and so on and
all
so.
the way up to,
All up to 1,000, right.
and that will take care of the rest.
Right. But you should not think sieve is very small because of this reason. No. Assume that you are sieving with factor 2. Then how many numbers should you strike out? 500,000 numbers you should strike out. So I didn't mean it's easy. I only meant the factors that you need to consider is between 1 and 1,000. And the next thing that I want to consider is this thing. But if you still have any doubts or questions or suspicions about the reason why, then I can spend more time to explain real details. So if you want to know deeper and deeper, ask me. I don't mind. If you want to know the reason why, we can stop at square root of n, then you can ask me. No? Because, as I mentioned before, this chapter is so tough. If I cover very many things, then you may have difficulty to observe, right, or to digest. Binary confirmation. Everybody here understands the reason why I should sieve from 2 through 1,000, nothing more than 1,000. Everybody here. But what about this number? What about this number? Or I can make it harder by adding this kind of, oh, it is over that, right? So I can remove it. What about this kind of number? It is between 1 and 1 million. Then why shouldn't we consider this number? Excuse me?
Factor 3.
I tried very hard to avoid it. Thank you. What about this number? Why shouldn't we consider this kind of number? So let's check it. I will open, because hand calculation is limited and we didn't learn the high-tech method yet. I will just rely on computer algebra system. So 1, 1, 1, 1, 2, 1 is prime, right? Computer said so, right? So I believe MATLAB. So this is prime. The teacher said we need to only consider the factors 2 through 1,000. But what about this number? The teacher was wrong. Was teacher wrong or your understanding wrong? So I want to know whether you really understand the situation or not. I was not wrong when I mentioned it, but you might understand it incorrectly, then you might think the instructor said wrong. So please check why this thing happens and how can you describe this kind of situation of having some big number which is prime. Right, that is it. Great. So assume that we strike out. We don't strike out the first appearance, right? So this could be the first appearance. Then the second appearance of this number is somewhere in between 2, 2, 2, 2, 4, 2, right? Then this number does not strike out this number, but one number strikes this out. 2 strikes this out. In other words, this should have some pair that is smaller than square root of n. That small number strikes this out. It doesn't strike out this prime number, but it strikes out this number. That's the reason why it's possible. Right? Because any number that is greater than square root of n should have smaller factor here. So if the number itself is not struck out, but the number like this should be struck out, right? So we could remove all the non-prime numbers this way. Then later we see, then we may have pretty large numbers such as almost 999, and then something could be prime, right? We still get this kind of big prime number. So you should not be confused. What I mentioned about sieving, I mentioned that we should only consider factors from 1 through 1,000 when we consider sieving. But it does not mean all the primes are there. No. Primes are scattered all over 1 through 1 million. But all we need to consider in factors is the set from 2 through 1,000. After that, we don't have to sieve.
Now, what if we wanted to know how many primes were
Great.
a specific number? How
So,
primes are less than 1 million?
yeah. So that is called very, very important theorem, prime number theorem. Gauss considered the greatest mathematician of all time. And he got some data, and then with statistical data, he concluded that the number of prime up to n, so the number of prime up to n, the number of primes up to n is approximately equal to n over log n. Here log means ln, but in number theory we don't use ln, just we use log, log. So, and this is called the prime number theorem. Very famous theorem, and initially Gauss conjectured this thing, tried to prove, couldn't prove, and later very famous mathematicians tried to prove, couldn't prove. About 100 years ago, two people proved this thing, and this is very celebrated theorem, prime number theorem. And in fact, do you know what? I will go there and then show you some problem. Do you see it? You asked, right? This is it. Very, very famous term. The number of primes up to n is roughly this one, but this roughly means when n goes to infinity, when n is very, very large. So it is not for small n. Any other questions?
I have a question.
Yes.
What you did on that lab to test is a prime. Do you know of any way to do it on a TI-85?
We will learn about Fermat theorem. Then Fermat theorem requires multiplication of big numbers with like power of 10,000 or more. That means like 2,000 multiplied 10,000 times, something like that, to check whether it's prime or not. That's the reason why usually hand calculators may not be able to handle this prime function. And later we will learn about that kind of primality test. Any other questions? So now I will go to the next part, because we are sieving using factors 2 through 1,000, and then after sieving using the numbers 2 through 1,000, we don't have to sieve anymore. In other words, you don't have to sieve using the number 1,001, and then you don't have to sieve using number 1,003 or 2. Why not? Because assume that this has some composite number, right? Then the composite number should have, for instance, this number multiplied by some k, which is less than this number. Then the consideration of sieving with k took care of this number already. That's the reason why we don't have to sieve this thing with the number bigger than square root of n. Yes?
So if this were a test question, that would be our answer. The reason we don't need to go look any further than the factor of 1,000 in this case, because those factors between 1 and 1,000
take care of all the composite numbers, right? Yes. Yeah, all the composite, not the primes, but the composite numbers are taken care of. And we leave prime numbers in the place, right? You still should not touch prime numbers in this sieving, right? Yes. Yes, right. And then, now the next important thing is this. Euclid found this thing. Do you know when Euclid lived? Euclid lived around BC. I do not know. I'm not good at history, as you know. Of course, I'm not good at many things. what else? I don't promote this thing. I want to find the result. It's right here. BC 300. BC 300 he lived. This means it's a pretty old theorem. There are very many prime numbers, right? How many? Infinitely many prime numbers. This is the Euclid theorem, right? There are infinitely many primes. So, knowing the fact is one thing, proving is another thing, right? And that is more important. So, proving. So, on the exam, I will ask you to prove whether square root of 2 is rational or irrational, or prove that it's irrational, and prove that this is true. Then what should you do? Mostly, as I mentioned before, proof by what? Contradiction. So let's begin. Assume not, right? Always assume not. But because it's so obvious, in most proofs, people don't even write down this thing, right? People don't even write down this thing. People write down the result of assume not, right? The result of assume not is what? Result of assume not is, right, assume that there are only finite number of primes P1, P2, up to Pn, no matter what capital N is, right? Assume that these are the only possible primes, right? In other words, in the world, we cannot find any more primes than these things. In other words, if we can find more than these things, then it's not necessarily finite, right? Do you understand what I mean or not? This assumption is the key. So assume not is translated. So assume that we have only just that many primes, nothing more than that. One more than that, then we can increase capital N. 5 more than that, then we can increase 5. So we can contain any possible finite addition by increasing the size capital N, right? Do you follow me? So this has all possible primes. Then I will lead to a contradiction. Consider P. Consider then, right? Then, and then this is lowercase. Consider P is P1, P2, up to every number, every prime of Pn multiplied plus 1. So consider capital P. Then, so let's find the GCD. GCD of capital P and then P sub any number K equals GCD of P sub K, and then if we use division algorithm, capital P divided by P sub K gives us the quotient and the remainder, right? What is the remainder? If you divide P by P sub, for instance, 1, then the quotient is this portion and the remainder is what? 1. So the remainder, right? This one is the remainder. Then what is GCD of one and other number? Always 1, right? GCD of one and other number is always 1. So we have the GCD equal to 1. What does this mean? What does this mean? It means PK, prime PK does not divide P. Because GCD is 1, then it doesn't mean, because if it divides P, then it should have GCD greater than 1, because P is prime, P is not 1. PK is not 1. So I came to this conclusion. So take a look. This P is not divided by any prime number. Then what is the definition? That is prime, right? The only possible divisor of capital P is P itself and then 1. 1 and P are the only possible primes. Why? Because all the prime numbers in the world cannot divide this P. In other words, P is prime, but I said only P sub n is the possible prime numbers, and I found one more number. In other words, that limitation led to a contradiction. So I will emphasize this part using red mark. Right? P is another prime. That didn't belong to P1 through Pn. I said there are only prime numbers 1 through P capital N, but I found one more prime. Contradiction, right? I will use the symbol. Two trains are coming against each other, right? Contradiction. Mathematicians use this. A contradiction. That's the end of the story. Kind people write down the statement one more time. Some people just stop right here. Some people do not even bother to write this thing. I had a professor at Illinois, at University of Illinois, just writing this way. Anyway, it's okay. Or even a word is okay. Or a contradiction. So thus, there are infinitely many prime numbers, right? So in any case, I completely proved that there are infinitely many prime numbers. Is this the only proof? No, there are many other proofs. But as you chose before, I will continue. So please browse the idea from the beginning to the end and then ask questions. After doing this, some people say this kind of thing. Oh, my teacher said 1 plus prime number 1, prime number 2, prime number 3 up to prime number n is prime. My teacher said that. Did I say this? No. I have a proof that he said that. Look at this part. Look at this part. He said P is prime. He said that, right? No, I didn't. I said this only under this assumption. I said this only under this assumption, not out of this context. Do you know what I mean? So you should not extract and say, he said. So I did not say that P multiplying 1 through 1 and then this product is prime. I didn't say that. I said, assuming that P1 through Pn are the only primes, then this should be prime. If this assumption is not correct, then this conclusion is not correct. Do you know what I mean? So I did not say this is prime. So I will show you. Is prime 1 plus 2? Okay, right? Is prime 1 plus 2 multiplied by 3, right? Still okay, right? The next prime is what? 5, right? Still prime. Oh, my instructor could be a genius, right? He said something that computer still prime, right? No. Yeah. So as you can see, once it reaches 13, so as you can see, once it reaches 13, it's not prime. then why is it not prime? Because of this reason. If we assume that there are only finite number of primes, then we can find something outside. But if there are many primes, then some number in between may devise the number. In the previous consideration, we couldn't consider that because we assumed that there are only these many prime numbers. But now, there could be some prime bigger than Pn, but smaller. In other words, there is a huge gap between these two numbers, right? There is a huge gap. There are many, many numbers in between, right? There are many, many numbers in between. We didn't consider these numbers in between in this consideration because of the strong assumption. We assumed that there are only finite number of primes stated here. Because of the statement because of this top strong assumption, we couldn't have any freedom to consider the numbers in between. But in real consideration, there are many prime numbers in between. So let's factor this. And as you can see, 59 exists, right? 59 and 509 exist in between. So take a look and then check what I am saying. Teacher said this is prime. No, I said if we assume that there are only finite number of primes from 1 through 13, I mean 1 through some number like this, and then there is no more prime. In other words, there are numbers, all these numbers are not primes. That was my assumption. Then this is the next prime. But in reality, there are more than these primes. In other words, there could be this prime, this prime, this prime. In other words, let's consider this situation. Assume that we considered, I will use the next space. So assume that we consider 2 through 13. Then assume that these are the only possible primes. Then the next number that I can write down is this number, 30031, right? Then, under our assumption, this is the next prime. Because what? I said there are only these many primes. Then, this is still a prime. Because these are the only possible primes in my proof, right? But unfortunately, that statement's wrong. In other words, there are more primes in between, such as 59, 409, right? Whether these are prime or not is not very important, but these kind of numbers exist in between. These numbers were overlooked in our proof because of our strong assumption. But if we lift that strong assumption, then we should put everything on table, right? These kind of numbers in between, right? So these kind of numbers could be the factor of this. In other words, this is not necessarily prime. So I will pause and then you can check and ask a question. And in fact, some people considered the possibility of getting primes in this direction. In other words, if you multiply 2 through some number, will it be a prime? Will it be a prime? Will it be a prime? They consider this kind. And they use many computers in the world and connect them and network them and then find possible primes. Some number is not prime, some number is prime. As you can see, this number is prime, right? This multiplying 2 numbers is prime, multiplying 3 numbers is prime, right? Multiplying 4 numbers here is prime, 5 numbers is prime, right? And then, as you can see, 6 number is not prime. So people investigate this direction using computing power, right? Using supercomputer or PC and connection, people consider this. Because we don't have enough time and I don't want to cover too many things, I will pause and then you may approach and ask questions. And you may leave the room if you don't have any question.